Hey, AP Chemistry. This time we're going to take a look at Chapter 4, Aqueous Solutions. We're going to split this into 3 different parts. One, just what are aqueous solutions, including electrolytes, precipitation reactions, solubility rules, and net ionic equations. Then we'll take a quick look at acids, bases, which we will cover way in depth later on in the year. And then we'll do the math portion of this unit, which is molarity, dilutions, and titrations. Let's just cover a few definitions first. An aqueous solution is the solution in which water is the dissolving medium. A solution is simply a homogeneous mixture of 2 or more substances. The solvent, I love how the book defines this, it's the substance that is in the greatest quantity. Usually the solvent is whatever you're putting the stuff into, which in most cases is water. The solute is the thing that's being dissolved. So the solvent could be water, with the solute being salt or sugar. Pure water does not conduct electricity. Tap water does. Why? Tap water has ions. It's the ions that conduct electricity. So an electrolyte simply means a substance whose solution contains ions. If a solution has ions, it's an electrolyte because it can move electrons. It can conduct electricity. A non-electrolyte is a substance that does not form ions. This would be like sugar. And dissociation is just a fancy way of saying it breaks down. Let's just take a quick moment to think about what exactly happens when a substance gets dissolved in water. And this is important because it's going to be on one of our labs. The first thing that has to happen is an ionic compound breaks apart. So imagine you have sodium chloride. You have to come between the sodium and the chlorine and break them up. So you have to overcome the attraction between those 2 ions. Then the water molecules need to be separated. You know, water molecules have hydrogen bonding, so they stick together as well. So first, break up the ionic compound. 2, break up the waters. Then the waters can surround the ions. This is what we call solvation. Most molecular compounds dissolve in water, like sugar, but they're not electrolytes. Ionic compounds break down, dissolve in water, and conduct electricity. There is one exception to the molecular compounds, and those are acids. Acids, especially strong acids, break down to form electrolytes. Quite often in chemistry, we use the terms strong and weak. And a lot of students think strong acids or strong bases mean that they have a really high or really low pH. Honestly, all strong means is that the substance completely breaks down into ions. Weak, not so much. So a strong electrolyte is the solute completely breaks down into ions. These contain all water-soluble ionic compounds. A few molecular compounds, your strong acids like hydrochloric acid. And when you're talking about something that is a strong electrolyte or a strong acid or a strong base, we use the single arrow in the equation to show that it goes to completion. Weak electrolytes don't break down as much. Now they do make some ions, but not very much. I mean, we're talking like maybe 1.8 times 10 to the negative 5th, not very many. Most of it just remains neutral molecules. Some examples would be vinegar, acetic acid. And because these don't break down all the way, when we write an equation, we use the reversible arrows, meaning that it's a reversible equation and equilibrium rules apply. So let's get into a little bit of fun chemistry. Precipitation reactions. All that means is that when you put 2 substances together, you get a solid. Usually 2 liquids and you wind up with a liquid and a solid. In regular chemistry, we do that experiment where you take the 2 clear liquids, you put them together, and you get that yellow solid that looks like yellow paint. So a precipitation reaction simply means that you produce an insoluble product, a solid. A precipitate is an insoluble solid that's formed by a reaction. Soluble simply means it dissolves. Insoluble does not dissolve. Why? And it goes back to what we were just talking about. If two ions attract each other more than the water molecules can separate those ions, the substance will not dissolve. So if two substances would rather cling to each other than get pulled apart and surrounded by water molecules, it doesn't dissolve. On the essential knowledge test, some of the questions had to do with solubility. So I know you've seen this before, but you really do need to memorize this if you have yet to do so. How do you know if something is going to be a solid? You got to know your solubility rules. This is a recreation of the table on page 129 of your book. If an ionic compound has nitrates, acetates, chlorides, bromides, iodides, or sulfate ions, they are soluble. All nitrates are soluble. Now there are some exceptions. So all nitrates, all acetates, soluble. Chlorides, bromides, iodides, most of the time are soluble. If they have silver, that particular mercury, remember mercury's got that other weird ion, or lead too, they're not soluble. If you have sulfate ions with either strontium, barium, mercury, or lead, they are not soluble. The insoluble ionic compounds have sulfide, carbonate, phosphate, and hydroxide. So if you have any ionic compound with sulfur, normally they're insoluble. They will make a solid. Most carbonates will make a solid, most phosphates, most hydroxides. There are some exceptions. Now in this case, that means they will be soluble. So if you have sulfur with ammonium, any of the alkali metals, that's from column 1. If you have sulfur with calcium, strontium, or barium, so that's column 2, those heavier elements, they are soluble. Same thing for carbonate. If you have carbonate with ammonium or anything from column 1, it's soluble. Phosphates, same thing. Hydroxide with ammonium or hydroxide with column 1 or hydroxide with those heavier ones from column 2, they are soluble. You need to memorize these. You need to come up with a way, and this will be part of a DQ question we have, finding a way to memorize these. I know most of you can write the products of a double replacement reaction. Remember the double date swap? That's pretty easy. The two positives switch places. Make sure you look at your charges and you write your formulas correctly. But the question is, in a double replacement reaction, we know one of the products is a solid, but which one is the solid? So you need to be able to predict which one will be the solid. And this is where those solubility rules come in. Well, just an FYI, the book refers to these double replacement reactions as metathesis reactions. They're just exchange reactions, like AX plus BY, and you get AY plus BX. Well, how do you know there's going to be a precipitate? Here's what you need to do. Look at your reactants. Note the ions that make up those compounds. So NaCl. Oh, I have Na and I have Cl. If you have maybe NaC2H3O2, you need to know that you have sodium with acetate. So be able to look at the formulas and break them apart into the ions. So consider which ions are going to go together as the products. This cation with this anion, that cation with that anion. Then you have to apply the solubility rules. And whichever one is not soluble will be your product, will be your solid product. So to complete and then balance a metathesis reaction, again, look at the ions present, switch places. You have to look at your charges. This is where people get it messed up. They forget about the charges, they don't write the formulas correctly, and then they can't get it to balance. And then go back to your solubility rules. Find the one that is not soluble, mark it as a solid. Make sure you balance the equation correctly. The last thing I want to cover in this PowerPoint is just the different types of equations we're going to talk about up to this point. A molecular equation shows the chemical formulas. This is what we normally write. A complete ionic equation shows everything written as ions. That is, anything that should be written as an ion. Anything that says aqueous, AQ, it can be written as ions. We don't write solids as ions. We don't write gases as ions. A net ionic equation only shows the ions and solids and maybe gases that are in the reaction. What happens is you actually eliminate the spectator ions. Think about a basketball game. The people sitting in the stands, yeah, they're cheering for the team, but won't the game go on without spectators? Yeah. Spectator ions, they're there. They're watching the reaction take place. Yay, go team! But they're not doing anything, so we can eliminate them. So how do you write a net ionic equation? It seems intimidating, but it's not. Write the balanced molecular equation. Anything that says AQ, rewrite it as an ion. Now you have to pay attention to coefficients and subscripts. Then look at the right and the left sides of the equations. Identify any spectator ions. If you have two NAs on one side and two NAs on the other side, get rid of them. Rewrite what's left. That's your net ionic equation. So here's a quick little example. Now, if you notice, 3 of these substances are aqueous, 1 is a solid. Anything that says aqueous gets broken down. So PbNO3, we break that into lead ions and 2 nitrate ions. Please notice that lead has a charge. Nitrate has a charge. Now, why are there 2 nitrates? Well, every time you break up PbNO3, you get 2 nitrates. 2Ki, you're going to make 2 potassiums and 2 iodine ions. You have to show these as ions. Don't leave the charges off. We don't break PbI2 down, it's a solid. And then 2KNO3 breaks into 2 potassiums and 2 nitrates. So notice I struck out the potassiums and the nitrates. They occur on both sides. That means they are spectators. They are there, but they are not actually reacting. What actually is happening? You have lead ions combining with iodide ions to make lead iodide. That is your net ionic equation. Now go tackle the homework and the DQ questions on this unit.